The research focuses on transcription-only supervised text spotting, which aims to detect text in scene images using only text transcriptions without boundary annotations. This approach eliminates the need for expensive boundary annotations. The authors propose WeCromCL, a model that conducts atomistic contrastive learning to model the character-wise appearance consistency between a text transcription and its correlated region in the scene image. This method is in contrast to typical cross-modality contrastive learning methods that focus on holistic semantic correlation. WeCromCL detects anchor points for transcriptions in a weakly supervised manner and uses these points as pseudo-location labels to guide text spotting. The model outperforms other methods on 4 challenging benchmarks, demonstrating its effectiveness. The research also compares WeCromCL with other methods, including TCM, OCLIP, and VLPT, highlighting the advantages of atomistic contrastive learning in transcription-only supervised text spotting. We propose a novel approach to transcription-only supervised text spotting, decomposing the task into 2 stages: weakly supervised text detection and single-point text spotting. The first stage, detecting the anchor points for transcriptions without location annotations, is particularly challenging and crucial for the performance of text spotting in the second stage. To address this, we formulate it as a weakly supervised cross-modality contrastive learning problem and design a simple yet effective model dubbed WeCromCL. Unlike typical methods for cross-modality contrastive learning that focus on modeling the holistic semantic correlation between a text description and an entire image, our WeCromCL conducts atomistic contrastive learning to learn the character-wise appearance consistency between a text transcription and its correlated region in a scene image in a weakly supervised manner. This is achieved by designing a soft modeling mechanism to learn an activation map by measuring the appearance correlation between a transcription and each pixel of a scene image. The activated region in the scene image is identified as the anchor point for this transcription and is associated with the transcription for contrastive learning to optimize WeCromCL. Without the location annotations for text, our WeCromCL can still detect each transcription effectively. The rationale is that a transcription acts as a cluster center that associates all matched images containing it, and the model is optimized to learn the similar appearance pattern for this transcription among all associated images, leading to precise location of transcriptions via learning the activation map. To conclude, our contributions are summarized as follows. 1. We decompose the task of transcription-only supervised text spotting into 2 stages, including weakly supervised text detection and single-point text spotting. Then we formulate the first and also challenging step as a cross-modality atomistic contrastive learning problem in an weakly supervised manner. 2. To the best of our knowledge, we are the first to define and investigate the weakly supervised atomistic contrastive learning problem between image and text modalities. We particularly propose a simple yet effective method for it, called WeCromCL, which can learn an effective cross-modality character-wise consistency metric between a transcription and its visual appearance in a scene image, thereby detecting the correlated image regions for the transcription without annotated text boundaries. 3. Leveraging the predicted anchor points by our WeCromCL as pseudo-location labels, we learn an effective single-point supervised text spotter adapted from SRSTSv2, a state-of-the-art text spotter. Integrating the proposed WeCromCL and the learned single-point text spotter, we construct a powerful system for transcription-only supervised text spotting, which compares favorably with existing methods on 4 challenging benchmarks. The proposed transcription-only supervised text spotter, WeCromCL, consists of 2 stages: detecting an anchor point for each text instance as a pseudo-location label, and conducting text spotting under the supervision of obtained pseudo-location labels. This method circumvents the limitations suffered by previous transcription-only supervised methods due to the lack of text location annotations. The first stage involves weakly supervised atomistic cross-modality contrastive learning, where the task is formulated as estimating the location for each transcription to serve as pseudo-location labels for supervised learning of a text spotter. The correlation between an image and a text transcription is represented as C equals F M O.I T, where M is an activation map indicating whether the corresponding pixel is associated with the transcription, T WeCromCL addresses two crucial challenges. Effective modeling of F entails precise estimation of the activation map M in weakly supervised learning without the ground truth, and learning the atomistic correlation between a text transcription and its visual appearance in the correlated region in the scene image. The proposed model employs an image encoder and a text encoder to learn latent embeddings for the input image and text transcription. The architecture of WeCromCL is shown in Figure 2, where the image feature and text feature are extracted and then fed into a cross-modality cross-attention module to predict the activation map M and the correlation C. The obtained anchor points are used as pseudo-location labels for optimizing the text spotter in the second stage. This novel approach enables the detection of text and images without relying on location annotations, providing a significant advancement in the field of text spotting. WeCromCL is a novel model designed to address the challenges of cross-modality learning in image and text transcription pairs. It uses a soft modeling mechanism to learn activation maps and a character-wise text encoder to tackle the issues of inconsistent transcription lengths and varying character appearances. The image encoder employs BIFPN and deformable transformer encoder to extract multiscale convolutional features. The text encoder is devised similar to OCLIP, learning individual vectorial embeddings for each character in the alphabet and incorporating temporal sequence information among characters. The key to estimating the activation map is measuring the appearance correlation between the transcription and each pixel of the input image. This is achieved through a soft modeling mechanism that uses cosine similarity in a projected feature space. The learned activation map is continuous, easing gradient propagation and preserving richer similarity information than hard representations. Following the activation map estimation, the correlated features in the image are aggregated to the text transcription for subsequent contrastive learning. This process involves cross-modality cross-attention operation, where the encoded transcription feature serves as the query and the all pixels of encoded image feature serve as the keys and values. WeCromCL performs cross-modality contrastive learning between the learned correlated visual feature and the encoded transcription feature to optimize all modules jointly. Negative pairs are constructed in two ways: either pairing the image to multiple unpaired transcriptions or pairing the transcription to multiple unpaired images. The loss function is defined to maximize the cosine similarity of positive pairs while minimizing the similarity of negative pairs, utilizing a negative sample mining scheme to introduce more challenging negative pairs and enhance the model's performance. The research discusses WeCromCL, a novel approach for cross-modality character-wise consistency metric learning between image and text. It utilizes atomistic contrastive learning to detect correlated regions in images and transcriptions. The model learns to recognize similar appearance patterns for each transcription by minimizing the similarity between negative pairs. This is achieved through a loss function that combines image-to-text and text-to-image constructions. The rationale behind WeCromCL is to prevent the model from collapsing to a uniform pattern for different transcriptions. The most activated position in the activation map is identified as the anchor point for the corresponding transcription, used as a pseudo-location label for learning the text spotter. The text spotter is instantiated with SPTS and SRSTS v2, demonstrating the effectiveness of WeCromCL. Experiments are conducted on several benchmarks, including ICDAR 2013, ICDAR 2015, Total Text, and CTW 1500, using evaluation protocols suitable for the method. The results show the potential of WeCromCL in enhancing modeling robustness and improving text spotting performance. In the realm of weakly supervised text detection, WeCromCL is a novel approach that leverages atomistic contrastive learning to identify transcriptions within scene images. This method differs from holistic contrastive learning, as employed by OCLIP, in its focus on character-level correlations between a transcription and its visual representation in the image. The effectiveness of WeCromCL is demonstrated through ablation studies, which reveal that the character-wise text encoder and negative sample mining scheme are crucial components of this model. WeCromCL outperforms OCLIP significantly on all benchmarks, showcasing the superiority of atomistic contrastive learning over holistic contrastive learning. Furthermore, when used to train SPTS, WeCromCL plus SPTS surpasses NPTS in all evaluation dimensions, particularly excelling in scenarios without the use of lexicons or with generic lexicon. This underscores the potential of WeCromCL as a tool for generating high-quality pseudo-labels for transcription detection tasks. The ablation studies conducted on different text encoders and the negative sample mining scheme provide insight into the design choices behind WeCromCL. By comparing the character-wise text encoder of WeCromCL with the token-wise text encoder of CLIP, it becomes clear that encoding text at the character level facilitates the learning of character-level correlations between a transcription and its visual representation in the image. Additionally, the negative sample mining scheme yields large performance gains, demonstrating its importance in the training process of WeCromCL. Overall, WeCromCL represents a significant advancement in weakly supervised text detection, offering a new perspective on how to leverage contrastive learning for this task. Its ability to generate accurate pseudo-labels for transcription detection tasks makes it a valuable tool for researchers and practitioners in the field of OCR. The authors propose WeCromCL, a novel transcription-only supervised text spotting method that efficiently generates pseudo-location labels from text-image pairs without annotation cost. The effectiveness of WeCromCL is demonstrated through visual comparisons of corresponding attention maps in the decoder, showcasing its superiority over single-stage methods like NPTS. The authors further investigate the impact of WeCromCL on fully supervised spotting methods. By pre-training SRSTS-v2 on curved synthetic dataset and fine-tuning it on varying proportions of ICDAR 2015 GT and fixed amounts of pseudo-labeled data, they observed that WeCromCL can improve the recognition performance of SRSTS-v2, especially when annotated data is limited. The results reveal the significance of the two-stage modeling strategy of WeCromCL over single-stage methods. Qualitative results of the transcription-only supervised text spotter on ICDAR 2013, ICDAR 2015, total text, and CTW 1500 datasets are presented, showcasing the estimated anchor points and sampled points. Quantitative results are also provided in Table 5, comparing the performance of WeCromCL plus SRSTSA with other fully supervised, semi-supervised, and transcription-only supervised methods. The results demonstrate that WeCromCL plus SRSTSA achieves superior performance when compared to other transcription-only supervised methods, surpassing NPTS and TOS by 16.4% and 9.2% on ICDAR 2015, respectively. The authors attribute the improved performance to the efficient generation of pseudo-labels by WeCromCL, which enables the model to learn from a larger dataset without additional human annotation cost. The results also highlight the significance of fine-tuning on real-world data pseudo-labeled with WeCromCL, which bridges the gap between synthetic and real-world data distributions. Overall, WeCromCL demonstrates its effectiveness in enhancing fully supervised spotting methods and achieving state-of-the-art performance in transcription-only supervised text spotting. The research proposes a novel approach to text spotting, decomposing the transcription-only supervised text spotting into two stages. The first stage involves detecting anchor points for text transcriptions as a weakly supervised atomistic contrastive learning problem across modalities. The method dubbed WeCromCL is designed for this stage, which is crucial and challenging. The detected anchor points are then used to guide the learning of text spotting. The system is trained on fully annotated synthetic data and transcription-annotated real-world data, outperforming existing methods like TOS and NPTS. The effectiveness and robustness of WeCromCL are demonstrated through extensive experiments on challenging benchmarks. The method's limitations include requiring high-resolution input images for detecting small texts. The research was supported by several grants and foundations. The research paper presents a comprehensive overview of recent advancements in scene text detection and spotting. It discusses various techniques and algorithms, including Mask Text Spotter v3, Textboxes++, and ABCNet, which are designed to improve the accuracy and efficiency of text detection in images. These methods leverage deep neural networks and propose novel architectures that can handle complex text shapes and orientations. The paper also covers the use of focal loss for dense object detection, as well as the development of single-point scene text detectors like SPTS and SPTS-V2. These approaches aim to simplify the text detection process by eliminating the need for anchor boxes or proposal networks. Furthermore, the authors discuss the importance of vision language pre-training for boosting scene text detectors. This involves leveraging large-scale datasets and using contrastive learning to learn transferable visual models from natural language supervision. Additionally, the paper highlights the role of weakly supervised learning methods, such as language matters, which utilize vision language pre-training to improve scene text detection and spotting without relying on strong annotations. The authors also provide insights into the limitations and future work in this field, including the need for more robust and efficient algorithms that can handle diverse text shapes, languages, and environmental conditions. They emphasize the potential benefits of integrating multiple modalities, such as audio and vision, to further enhance text detection capabilities. Overall, the paper offers a thorough review of state-of-the-art techniques in scene text detection and spotting, shedding light on the challenges and opportunities in this rapidly evolving field. The paper discusses the development of a novel text spotting system, WeCromCL, which utilizes weak supervision and adapts the SRSTS model to improve performance. The system consists of an image encoder, anchor estimator, sampling module, and recognition module. It has been modified to drop the detection branch, incorporate practical techniques from Deep Solo, and use focal loss for optimizing the anchor estimator. This adaptation is denoted as SRSTSA. The authors provide implementation details for WeCromCL, including pre-training on synthetic datasets, fine-tuning on specific real-world datasets, and the use of data augmentation strategies. The learning rate and other hyperparameters are also specified. In addition, the paper presents an ablation study comparing the pseudo-label quality generated by WeCromCL with other weak supervision methods, such as OCLIP and NPTS. The results demonstrate the efficacy of WeCromCL in generating high-quality pseudo-labels for text spotting tasks. Overall, the paper contributes to the advancement of text spotting systems by introducing a novel weak supervision method that adapts and enhances existing models, leading to improved performance in real-world applications. Here is the combined summary of pages 21 and 22. The authors present a comprehensive evaluation of their proposed WeCromCL method, focusing on the spotting task on the ICDA ART 2015 dataset. Table 2 compares the performance of different pseudo-label generation methods and ablation conditions, showcasing the effectiveness of WeCromCL. Notably, the PSE point method, which utilizes text-only annotation information, achieves competitive results. The impact of anchor quality on spotting results is investigated, demonstrating that the accuracy of WeCromCL is comparable to using ground truth anchor points. The authors also explore the effect of perturbing anchor points, introducing a perturbation degree alpha, and observe that the offset from ground truth follows a Gaussian distribution. This experiment confirms the high quality of WeCromCL's pseudo-labels and its effectiveness without relying on explicit position labels. The performance gap between fully supervised methods is attributed to two primary factors: pseudo-label accuracy and positional supervision method. The results highlight the importance of detailed positional information, with gaps of 2.7, 2.3, and 2.6 between ground truth point supervision and pseudo-labels supervision, and 2, 4, and 6.4 between box supervision and point supervision. To visualize the localization performance of WeCromCL, the authors present activation maps generated by the model in Figure 1. The results demonstrate WeCromCL's ability to handle complex cases, such as text with artistic fonts, curved text, long text, and small text. Given a text transcription, WeCromCL generates a corresponding activation map, identifying the highly activated region as the anchor point for the transcription. These visualizations showcase the effectiveness of WeCromCL in spotting tasks. In the context of text spotting, a novel approach is presented to leverage a transcription-only supervised method for achieving satisfactory performance. This method, WeCromCL, utilizes a deep neural network to locate text regions within images when given a text query. The process involves enlarging the input image to ensure accurate location of the queried text, regardless of its size or clarity. The visualization of text spotting results on 4 benchmarks: ICDAR 2013, ICDAR 2015, Total Text, and CTW 1500 demonstrates the effectiveness and robustness of this transcription-only supervised text spotter. Even in challenging cases such as tiny, fuzzy, curved, or long texts, the proposed method can successfully locate text instances and perform sampling for text recognition. WeCromCL's ability to locate text regions is visualized through activation maps, where the most activated pixel with the peak value in each map is identified as the anchor point for the corresponding transcription. These anchor points are then used as pseudo-location labels to supervise the learning of the text spotter in the subsequent text spotting stage. The visualization of text spotting results showcases the method's capability to handle various types of text instances, including those that are difficult to detect due to their size, orientation, or clarity. By leveraging a transcription-only supervised approach, this method eliminates the need for expensive bounding box annotations, making it a more efficient and cost-effective solution for text spotting tasks.